In this video, we will find the tangent plane to a surface which is given by an implicit equation as a level surface. So we've already seen before how to find the tangent plane to the graph of a function, but now this is different. Here, the surface is given implicitly, meaning it's given by an equation of this form, which is a function set equal to a constant. So unlike the case of a graph, where one of the variables is solved for, here all the variables are mixed together on the same side of the equation and it's set equal to a constant. And we'll write an equation for the tangent plane in this case. Now recall that to find the equation for a plane, you just need two things: a point on the plane, which we're given here, and the normal vector to the plane. So the key thing is that the normal vector to the tangent plane to a level surface is just the gradient of the function. So this thing that I called in blue, f, we just need to find its gradient vector at the given point, and we can use that as the normal vector to the plane. So first let's do that. Let's compute the gradient of this function. So recall, the gradient simply means the vector of partial derivatives. Okay, so let's compute these. So first, the x derivative. So for the first term, that's yz. And the second term is just cosine of x plus y plus z. And then the other three are similar. For y, we get xz plus cosine x plus y plus z. And for the z derivative, we get xy plus cosine x plus y plus z. And maybe just to make it slightly nicer to look at, let's break this up into two vectors, since we have a plus sign in each slot. Alright, this is yz, xz, xy, plus the cosine of x plus y plus z times the vector 1, 1, 1. Since cosine of x plus y plus z appears as the second term in all three slots. Okay, so in general, at a random point on the surface, this is the normal vector to the tangent plane. Well, we want it at this particular point, so let's plug in those values for x, y, and z. So we want to plug in pi over 12 for x, pi over 6 for y, and pi over 4 for z. Okay, let's do it. So y times z is pi squared over 24. X times z is pi squared over 48, and xy is pi squared over 72, plus cosine of x plus y plus z. Well, before we move on, let's notice here, well, let's just write it out first. Cosine of pi over 12 plus pi over 6 plus pi over 4 times 1, 1, 1. But notice that if you add all three of these together, it's pi over 2, and the cosine of pi over 2 is 0. So this term is just 0. And then if you notice, we can factor pi squared out of all 3 slots in this first vector. And we can actually do a little better. All the denominators are also divisible by 24. So we can actually pull out pi squared over 24. The first slot will be 1, second slot 1/2, and the third slot 1/3. So this is the gradient vector. So we can use this as the normal vector for our tangent plane. But actually, if you have a normal vector to a plane, any rescaling of that vector will also be a normal vector to the same plane. So in fact, just to make things simpler, we can ignore the pi squared over 24 and just use 1, 1/2, 1/3 as a normal vector. Since it points in the same direction, it's just a different length. So it's fine if you want to leave the constant on there, but just to make it simpler, I'm just going to use this. And now let's write the equation for the plane. So let's remember how we do this. So it's 1 times x minus the x-coordinate of the point, which is pi over 12, plus 1/2 times y minus, and the y-coordinate was pi over 6, plus 1/3 times z minus, the z-coordinate was pi over 4. And all that equals 0. And this is now the equation of the tangent plane at that point.